Just hold on. So, so the question was that convolve convolve x of n, which has been given to you as a sequence AB, with h of n, which is CD. Right? So this was the question given to you. So y of n, which is convolution of x of n with h of n, is written as summation over k equal to 0 to 1 only, because there are only two elements of both the sequences. So the summation doesn't go from minus infinity to infinity, it just goes from 0 to 1. X of k, h of n minus k. And the way we are going to think of it is, we will write x of k as frozen in place. So I'm going to freeze kb here. And I'm going to flip h of k around. So let me put a dot here. So this is corresponding to k equal to 0. This is k equal to minus 1. This is k equal to 1. So when I flip h of k around, it becomes like this, d, c, and then there is nothing. So y of 0 is going to be just the product of the elements which are in the same column. So here d gets multiplied with 0, b gets multiplied with 0, but a gets multiplied with c. So I get ac. For y of 1, what do I need to do? So this is for y of 0. For y of 1, what do I need to do now?
Move D and C to
Shifting.
rightwards.
Yeah, move d and c towards the right. So then this becomes null, this becomes d, and this becomes c. And I'm going to put one more null here also. So these dots are zeros. And so if I do element by element product, I get a multiplied with d. So now this is for y of 1. AD plus BC. And then finally y of 2, I move it one more time. So this becomes null, this becomes null. This is D and this is C. But then the only non-zero multiplier is B times D. And so now, therefore, sequence y of n is simply AC, that is first element, AD plus BC, which is the second element, and BD is the last element. So let me see if any. anyone give this answer or not? Sumit Monpara gave not correct answer. Bundit Makadia didn't give the right answer. Jill didn't give the right answer. Let's see who gave the right answer. Pujan also didn't give the right answer. Manan Benkara came close, but not it is not the right answer. Vandan, okay, Vandan gave, see, please. Yeah, so Vandan gave the right answer. So Vandan is first person I see who has given the right answer, and then who else? Pinak has done a reasonable job, but still it is not the right answer. Smith Bausar has done a reasonable job. Yeah, so apart, okay, Krish Gulbani has done good effort. Right, so Nishad Shah, no. Parek Kunj. Yeah, so many of you have attempted, but uh, possibly with the exception of one, then nobody gave this answer. Which means that either you have been sleeping while I was talking about convolution over last two lectures, or it hasn't sunk into you. Meaning that you haven't actually spent time on understanding this operation of convolution. So please do that, I think, before the exam at least. Okay, and then let me write here in the upper part. So we said what happens when A is equal to C and B is equal to D. So when A is equal to C and B is equal to D, the answer is trivial. Y of n is equal to A squared 2AB and B squared. Okay, now does this remind you of something, this particular form of Y of n?
A plus B whole square.
Yes, right. And so if X of n and Y of n, sorry, H of n, are interpreted as defining the sequences of coefficients of two polynomials let's say P of X, or actually because I have used the terminology X to denote a sequence, I won't use it to denote the variable of the polynomial. So I'll write it as the variable of a polynomial, I will make it Z. So P of Z is equal to AZ plus b. And q of z is another polynomial corresponding to h. And this I'm going to make it cz plus d. Then r of z, which is multiplication of these two polynomials, p of z and q of z, this will have the same answer that that we got. It will be a c z squared plus a d plus b c times z. Sorry, this is not a plus here. Sorry about that. See, this is a sequence, so there is a comma here. And then finally, we get BD. And therefore, when A is equal to C and B is equal to D, P of Z, sorry, R of Z, which is product of P of Z and Q of Z, it just becomes AZ plus B whole squared, which is no wonder A square Z square plus 2AB times Z plus B squared. This is our well-known familiar expression of expanding first degree linear equation to the power of 2. Okay, does this make sense?
Yes, sir.
Okay. So what we can say is that if we consider two polynomials, these polynomials you have been studying since your 9th grade or 8th grade even. We consider two polynomials. Let's say one is of degree n, which is P of z. Another is of degree m, which is Q of z. Then if you multiply these two polynomials, it turns out that R of z will have a degree of n plus m. Meaning that if I think of P and Q as sequences, the length of this sequence will be how many?
N plus 1.
N plus 1.
Of coefficient sequence will be n plus 1. And this will be m plus 1. And here it will be n plus m plus 1. But this is nothing but our formula that we have seen earlier for the length of the convoluted sequence, which is n plus 1 plus m plus 1 minus 1. So this is another way to see, kind of not a conclusive demonstration, but it kind of indicates to you that the multiplication of the two polynomial will give us, or the coefficients of the multiplication of the two polynomials is given by convolving these sequences corresponding to the coefficients of P of z and Q of z. Right? I don't know if you have started looking at the last lab. There is not much of programming that I'm asking you to do. It's more like a study of the convolution and all that, a study of the Fourier transform. Maybe you haven't had chance to do that, but please, again, as I said, try to do it before the exam. And so if you do that, you will come to grips with this particular aspect of the convolution. I mean, you can take this az plus b to the power 3, get that using convolution method, and then compare it with the answer that you know anyhow. Okay, you will see that they're going to be one and the same. And so it is no wonder that when we did the very first example of multiplying 123 with 113, we got the same answer through convolution as we got it using the standard multiplier, because you see 123 is actually a polynomial where that x or z is 10, right? I've written here 123 as a polynomial. I mean, we tend to become so familiar with such numbers, 2-digit, 3-digit, even 4-digit numbers, that we think of it as a standalone entity. But there is nothing like 123 in the real world, right? If you count 123 matchsticks from a matchbox, they are matchsticks. They are not actually number 123. 123 is a concept that is in our minds. And then that concept has been integrated in the calculators and computers and programming languages. But physical world doesn't have anything that is actually this 123. You can write it as 1, 2, 3, but what does it mean? Well, actually it is this polynomial where the variable is 10. And so when we multiply two numbers, we are actually doing polynomial multiplication, and then we are evaluating the value of that polynomial. And so that is why, just like what we saw earlier, the convolution can be used to multiply two numbers. Anyhow, it's something that we have already discussed, but this is kind of an aspect of convolution that I wanted to bring forward to you. So now let us get into something more related to communication, more related to engineering. And this is quite an interesting variation of what we have already seen. Okay. It kind of illustrates to us something quite, I would say, quite amazing about the convolution operation. So before I begin, what I want to mention to you is that typically, you know, when I multiply this P of Z with Q of Z, these coefficients R of Z that I get, R0, R1, R2 up to R of n plus m, they do not look either like the coefficients of P or coefficients of Q. Am I right? You see here, we took the two coefficient sequences as AB and CD. And when I convolved it, I got something like AC and then AD plus BC and BD. Nothing like the original two sequences. It kind of gets all jumbled up in R of Z. Here, the two sequences are AB, and again the same sequence, AB we are convolving with itself. Again, the answer is A square, 2AB and B square. It's not AB at all. So quite it's a curious property of convolution operation that there is one particular polynomial multiply that you can do, and once you think of it, it will become kind of obvious to you that yeah, it has to be that way. But in the textbook, if you come across this, maybe it is not always explained to you in the same manner. So maybe it becomes a little bit of a mysterious thing. But an interesting aspect of convolution is that there is one specific type of polynomial multiplication that you can do, for which the output of the convolution looks a lot like the input. It is like the input x of n pretty much came out at the output with some scaling. So if A input is AB, that's a sequence AB, the output will be maybe 0.5 times A and then 0.5 times B. So that for a very specific type of input, the convolution doesn't mess up the input. It kind of preserves the input, except that it scales it. Let us look at it. So h of z, I'm going to make it a full polynomial in z, and for some reason, I have made it power of negative k instead of h of k, z of k, z to the power k. I made it h of k times z to the power minus k. It's just a notational thing. Don't worry too much about it. The main point is that this h of z is like our q of z. I'm just writing it as a polynomial in variable z. Now, for x of n, I'm going to just make it z of n. Okay, so actually I should call it the polynomial corresponding to x of n.
Hello.
So this is capital X of z is nothing but z of n. And now if I compute the convolution, which is using this formula here, then for x of n minus k, if I substitute here instead of n, if I put n minus k, it becomes z of n minus k. So this formula becomes h of k times z of n minus k. And the summation, remember, is over this dummy variable k. Now, I can bring out z of n because it's a constant term. It doesn't get added over multiplier k, and so I bring it out and bring it out of the summation, and so I get z of n times this bracket. And inside this bracket, you will see that there is no dependence on the variable n, the time index n. Independent of what time index it is, and it is, this bracket remains the same. It is a summation over k of h of k, z of minus k. But that we have denoted it already as this polynomial, h of z, evaluated at z. Now evaluated at z minus 1, z inverse. And so you see that what I get at the output of the convolution is my input sequence x of n, except it got scaled by h of z. And h of z is a constant. It is independent of n. Right? So that is what I have expressed it by these boxes. The first equality came by simply substituting the expression of x of n in the formula for convolution. So that is how I got this first equality, or rather the second equality. The second one came because you can pull out z of n. It is a common term in this summation over k. And so we can kind of take it outside of the summation and multiply the summation with z of n directly. And then the third equality came because this term in the bracket is exactly how we had defined this polynomial evaluated at z inverse. So now the output is same as the input xn, except it got multiplied by h of z, which is just a scalar. Why it is a scalar? Because that is how I have defined it. I'm doing this summation. And when I have a bunch of values, I sum them up. I finally get just one number, one scalar. It may be complex valued in some cases, but still it's going to be just one number. It's not going to be a sequence. And so each value of x of n got multiplied by this h of z. This is called the eigen function of the convolution operation, this type of inputs. This input that we have considered the specific form of the input x of n is equal to z of n. Sorry, x of z is equal to z of n. That is called the eigen function of the convolution operation of the convolution, or in general LSI systems. So from something which was quite basic from your 9th grade algebra, we are now moving forward. We are talking about something which is more advanced. But the concept came directly from the algebra. You know, this math is very straightforward. Everyone here should be able to understand what is going on here. But the observation, the conclusion that comes out of math is not very, very obvious. Somebody who first came up with this observation, he or she must have been a very smart mathematician, because the conclusion that has to be taken away from this operation is that, unlike how it typically happens when you convolve two different sequences and you get a third sequence which is completely different from either one of them, in this case, the output of the convolution is a lot like the input. And then that type of input is a very special type of input, and that special input is labeled as eigen function or eigen input. Okay, so how does this help us? So let us look at one specific case when I made z equal to complex exponential in frequency f. Z is equal to e to the power j 2 pi f. And remember, x of n is z of n. So x of n became e to the power j 2 pi fn. Right? Z is this term. And so z to the power n is e to the power j 2 pi fn. But this is something that hopefully you remember from our earlier lectures. This is nothing but the discrete time complex exponential phasor. This is the type of signal that we used to up convert and down convert the modulated symbols. And this is the type of sequence that we use to do Fourier transformation in MATLAB. Remember, we went over multiple examples of Fourier transform. This is what I have asked you to do in Lab 9. And there, again, we have used this type of sequence, complex exponential. And so if we think of complex exponential as z to the power n, then what we saw earlier on the previous slide applies right away, which is what this entire derivation is. It's a repeat of what we already did on the previous slide. Okay, nothing new here. The only thing is that instead of z to the power n, I am making it exponent of j2 pi fn. These first two terms are directly from the formula of convolution, so I'm not going to go over them. In this third term, the third equality, I just substituted for x of n minus m, this expression. And so e to the power j2 pi fn became e to the power j2 pi fn minus n. Now, just like what I did on the previous slide, I pulled out f of n term, it came out here, but this is nothing but our x of n. So in the last line, I substituted x of n for that. The remaining part here, which is in the bracket, becomes h of f instead of h of z, because now this is a function of frequency f. Now, can anybody tell me what this h of f is? H of f is this summation. Does it ring any bell? We have done this summation earlier. Any thought?
Synthesis with h of m as weights.
Analysis.
Analysis.
Yeah, it is one of the two things, right? You are thinking along the right lines, but it can be either analysis or synthesis. The answer is it is the Fourier transformation. This is what we did. Remember, we were taking some sequences and we were multiplying with that G matrix. This is doing the dot product of one column of G transpose, which will give you this term, with the sequence that you are considering. And so this h of f will give you one element of that product G times h. It will give you the element at the particular frequency f that you are considering. Frequency f at which the input is oscillating at. So this h of f in the last term is the, I would say, discrete time, because there is a continuous time version of it also, discrete time Fourier transform of h of n evaluated at frequency f, where f is a variable. I can make f to be negative 100, negative 5, negative 0.1, plus 3, and so on. So depending on what f I take, I'll get a different value of h of n. But the point is that this x of n, which is this complex exponential oscillating at f, through the convolution operation comes out as it was before. Only thing is that it can get multiplied or attenuated by some scalar. And that scalar is nothing but the Fourier transform at that frequency, the frequency of the input. So now, now that that part is discussed, we can now start generalizing. Once you are okay with this concept, you can then take it for further generalization, and that gives you even more understanding, a deeper conceptual power. So I'm going to now say that input is not uh, oscillating at only one frequency. There are two frequencies, F1 and F2. And furthermore, I will say that this first uh, wave, first complex wave, has some weighting which I have denoted it as x of 1. The second one is multiplied by x of 2. Maybe x of 1 is 0.1. X of 2 can be 3. Some numbers. So the whole wave got shrunk to 0.1 for the first case, and for x2 it got amplified by 3. If you take a look at the real part of the first one, it's a cosine whose maximum value becomes 0.1. If you take a look at real part of the second term, it's again a cosine whose value at the peak is 3. And the input that I'm sending to the same convolution operation is just the summation of the two. It's a linear superposition of x1 and x2. So with that, if I do this convolution operation, I go through the same math. I can do the same trick that I did on the previous slide on individual x1 and x2 separately. And so what I will get is an output which is x1, except it got scaled by the Fourier transform of h of n evaluated at f1. And x2 got multiplied by the Fourier transform evaluated at f2. Okay. So obviously, if I generalize this further and say that the input is a linear superposition of a lot of different complex exponential, each oscillating at a particular frequency f of small k, where each frequency is additionally weighted by this weighting coefficients x of k. And then I just mix them all up. I do a synthesis operation. If I start thinking of x of n like this, then this type of x of n can be any sequence. Synthesizer here, this equation, will allow me to synthesize any x of n provided I appropriately choose these weighting coefficients. And this is the word synthesize should remind you, this is nothing but doing inverse discrete time Fourier transform of x of k, where x of k is in the frequency domain. So now if I pass this through the convolution operation, what do you think I'll get?
Summation of products at different frequencies. F1 to Fn.
When I did it for two terms, I got this result at the bottom of the slide. Each of the complex exponential function, which was getting weighted by x of 1 before and x of 2 before. Right? F1 was getting weighted by x1. F2 was getting weighted by x2. It additionally got further weighted by h of f1 and h of f2. If I extend it to this slide, what will happen?
Sorry, it will be summation of xi and weighted by h of fi.
Yes. X of I, where is I? I don't see any I in this formula.
Sir, I is index of xi and weighted by
Don't
fi.
introduce your own term. Use only the terminology that is here. I haven't put any I here. So please don't use that. All you have to do is see what happens with x of n comprised of two complex exponentials with these weights x1 and x2. What we see is that the convolution output is going to be the same two complex exponentials which are getting linearly superimposed, except they additionally got scaled by h of f1 and h of f2. Suppose instead of 2, if I have 3 complex exponentials, f at f1, f2, and f3, then what will be this output?
Here additional term that x3
There'll
and
be one, right, Pujan is correct. There'll be additional term here. It will be x3 of n multiplied by h of f3. If I have fourth complex exponential, there'll be one more term, x4 of n, h of f4. And so who can tell me now how to write the output for this general expression here?
Summation xkn into h of fk.
Correct, Kandarp. So Kandarp is correct. And then that has to be multiplied obviously by e to the power j2 pi fk of n, because that is how we are defining individual x1, x2. So that is the math that I have done here. So what happens is that the weight of this complex exponential at the input x of n, the weight was x of k. And we have called this x of k to be, what did we call x of k? If x of n, as I have written here, if it is obtained by synthesizing this complex exponentials weighted by x of k, then it means that x of n is the inverse discrete Fourier transform of capital X of k. And therefore, capital X of k is what? Capital X of k, therefore, has to be
Sir, may I answer?
Discrete time Fourier transform of x of n. If you can synthesize x of n from capital X of k, then obviously if you analyze capital X of k, you will get analysis output as capital X of k. Right? Synthesis and analysis are two backward forward type of operations. If we are agree to accept that I can synthesize this X of n, the time domain sequence, in this manner where I have to use the weighting coefficients X of k, then I have to also accept that if I am now, instead of X of k values, if I am now given the actual time domain sequence X of n, and if I try to analyze what are the weights of different complex exponentials that make up this X of n, I will obviously get capital X of k back. So analysis of X of n will give me capital X of k, which means that X of k is the Fourier transform of X of n. Okay, so who gets this? Let me ask somebody who has just recently answered. Kandar, do you understand what I'm saying here?
Yes, sir.
Pujan, what about you?
Actually, not much.
Not much. Okay. Isha, do you understand?
No, sir.
No. Okay. Yes. Okay, so looks like maybe a majority of you don't understand this. How about this slide? Let me ask this slide. Did you understand this slide? Or maybe even let me go one slide backward. How about this one? Did you understand this part? Isha?
Yes, sir. Yes, sir.
Okay. Pujan, do you understand this?
Yes, yes, Sadish.
This is
I
fine?
understand. Yes.
Then the same exact derivation I have done here by making the input to be comprised of two complex exponentials. And it's the same trick that I applied, same math that I did. And the answer became x1 h of f1, x2 h of f2. So Tarang, do you understand this part?
Yes, sir.
Let me ask somebody who has been a little quiet. Okay, so Ruchir Darji, do you understand this, Ruchir? Ruchir, are you there or you went back to sleep? Ruchir might have logged out. Darshan Dobaria. Darshan, are you there? Okay, so a lot of you are maybe not lot, but many of you are maybe just logging in and then going back to the bed and maybe snoozing your alarm or something. So the thing is that this is going to become of relevance to you in the next semester, I think. Next or the next to next. Because in some of the subsequent courses that you take, you will have to better understand these concepts of Fourier transformation and analysis, synthesis, convolution, etc. So that time, if you have already understood this part, then your life will become easier there. And the reason why we are going through this math now is because it will help us better understand one of the key theorems that we have studied earlier, the modulation theorem, Fourier transform. Anyways, we have only 5 more minutes or 10 more minutes left. So let me maybe repeat one more time that here, this equation, I can write it when I write it, when I have this expression of x of n, I can say that this x of n and capital X of k are related by Fourier transformation. If I go this way, then I'm doing ft, which is same as I'm analyzing. I'm analyzing the time domain sequence x of n and trying to determine what are the weights of different frequencies that it is made up of. And it turns out that in this particular case, when I do the analysis, I will find that x of n is made up of only 2 frequencies, f1 and f2. And those 2 corresponding complex exponentials are mixed up with the weights of 0.1 and 3. So that is the analysis viewpoint, or the Fourier transformation of x of n to get x of k. And therefore, as this equation says here explicitly, if I am given just the weights x of k, then I can synthesize x of n by doing the inverse Fourier transform, which is the synthesis viewpoint. Okay, so let me see, who should I ask? Tarang, are you fine with this?
Yes, sir.
Isha?
Yes, sir.
Okay. Pujan, what do you think? Is this
Yes, sir. Yes, sir.
okay? So then this is just the math. Okay, this is your high school math. There is nothing new here. This is just an extension of the previous slide, whose last line says that this y of n can be written like this, meaning that this original weights x of 1 and x of 2, they additionally got multiplied by h of f1 and h of f2, and those h of f1 and h of f2 are nothing but the Fourier transformation of the sequence h of n, because that is what this formula is. This is the formula for Fourier transformation. This is the formula for the analysis operation. Here we are analyzing h of n at frequency f1. Here we are analyzing at frequency f2. Same thing we did here. Here we analyzed h of n at frequency f, and therefore we called it the Fourier transform of h of n evaluated at frequency f. Turns out that on this slide, the convolution operation implicitly did that analysis for us, and it very appropriately multiplied x1, which is at oscillating at frequency f1. It dutifully multiplied the Fourier transformation of h at f1 with x1. Then it did the Fourier transform again of the sequence h of n at frequency f2, and it multiplied x2 with just that h of f2. Okay, so now this is the question that I will ask you. I'm going to write y of n here. Y of n is that output, right, on the previous slide. So given the example on the previous slide, for the example on the previous slide, I want to do this. Y of n, if I move towards the right, I do Fourier transformation. If I move towards the left, I do inverse Fourier transformation. And this is fill in the blank. Okay, so Kandar, what do you think this answer should be? Can you fill in the blank here?
I'm thinking.
Vandan, if you are there and if you have an answer, you can say it now.
Small x of n into capital H of x, H of f.
Sorry?
Small x of n into capital H of x. Sorry, H of f.
So Jamin actually is maybe on the right track, but except, remember, this is the time domain, and therefore over here we should see signals which are function of the time index n. Here it is frequency domain. After we do Fourier transformation, time goes away. We just are left with frequency domain, and so our answer should be indexed by the variable k, or f of k if you want. What I want you to think of about is that we are defining the Fourier transformation as the weights of complex exponentials. Weights of complex exponentials at different frequencies are the Fourier transform values at those frequencies. What I would like you to think about is that because of the convolution, what happens to those weights?
That's amplified.
They become multiplied with h of fk.
So Harsh is correct. This x1, which was the original weight, it got additionally scaled by h of f1. x2 was the original weight for f2. It got additionally scaled by h of f2. This e to the power j 2 pi fn came through without any change. See, this is e to the power j 2 pi f2. This is e to the power j 2 pi f1. And this is the original weight, x1, x2. Now they got additionally scaled by the scalar. But the scalar is what we have said, it is the Fourier transform here at f1, here at f2. So does this give you any hint of how to answer the question on the next slide? Harsh.
Sir, h of f.
You are saying the Fourier transform of y of n is going to be h of f?
And will it be capital X of k into h of fk?
And they give the right answer. So it will be think about it if you have understood this the way Kandar has understood it or not. See, the way to think about it is that this I can write it as x of 1 h of f1 times e to the power j2 pi f1n plus x of 2, capital X of 2, h of f2 times e to the power j2 pi f2 of n. But remember, the multipliers of this complex exponentials are what we are calling as the Fourier transform of the sequence x of n. If I take this sequence x of n, if I want to know what the Fourier transform values are, then I will have to determine this weights or the multipliers or the scalars that are affecting each of these complex exponentials. That is the analysis viewpoint of the Fourier transformation. When I analyze x of n, I will know what x1 is, what x2 is, and so on. And therefore, if I analyze this y of n, I will get this weights. I'll get x1 times h of f1 as a weight of the first exponential at f1. I'll get x2 times h of f2 as the weight of the second exponential at f2. But these weights are the Fourier transform themselves. And so if I look at what the weights are, they are x of k times h of fk. And that is generalized here. The weight of the complex exponential changes from x of k to h of fk xk once I pass this input x of n through the linear shift invariant system whose impulse response is h of n. Okay, so we are going to stop here. And I think I'm not 100% sure. I haven't looked at the dates yet. Your exams begin on 7th, right? 7th of next week.
Yes, sir.
So,
Okay, so we will have one lecture left in the semester on the 6th. And it will be a short lecture. The main thing that we will do is wrap up this topic of convolution and Fourier transformation in a short time. So we'll meet on Tuesday at noon and wrap up the semester, wrap up this topic, and wrap up CT111. Okay, so that is all from my side for today.